Hey everyone! In this video, we're going to be looking at an example where we're going to find the general solution to a separable first-order differential equation. What I want to start off with, though, is just talking about what a separable first-order differential equation is. So to do that, let's look at the example I have, and I can talk about each part in the definition of these differential equations. So here on the screen, I have an example of a separable first-order differential equation. So let's go through each word in that term, and I'll just talk a little bit about what that means. So the last one, differential equation, what that means is it's an equation that involves a derivative. So taking a look at my example, I have dy over dx, which is the derivative of y with respect to x. So because it contains a derivative, we call this a differential equation. The second to last one there, first order. So a first order differential, what that means is this is just the first derivative. If I were to have a second derivative, then it would be a second order differential and so on. So because this is just the first derivative for x and y, it's a first order differential equation. And then the last one, the very first part of this term, separable, what that means is I can take all the x's and the y's and I can separate them. So the dy and all the terms that contain my variable y, I can put those on one side of my equal sign, and I can do the same thing with the x's, putting them on the other side of my equal sign. So now that we have an idea on what this entire term means, separable first order differential equations, let's take a look at an example on how we can find the general solution. So what that means, though, if I'm going to find the general solution to a differential equation, what I end up getting is a family of equations that works for this equation. So in order to find that, we're going to separate the x's and the y's, and then we're going to take the integral of both sides, and then that's going to give us our general solution. So first thing is we need to separate the x's and the y's here. So on the left-hand side, dy over dx, I can multiply both sides by dx. That will simplify this fraction, moving that to the other side here. So why don't we just start off with that? So that's going to give me dy is equal to our negative 2x e to the y power, and then we have our dx. So now I got the negative 2x on the right-hand side. I have my dx on the right-hand side. So now we just need to move this e to the y. We want to move that over to the left-hand side so that all of our y's are grouped up. So to do that, we're going to divide both sides by e to the y power. And I'm going to rewrite this a little bit. So this is the same as 1 over e to the y, or we can think about that as e to the negative y. Then we have our dy, and then on the other side we got negative 2x times dx. So now, to find our general solution, we're going to take the integral of both sides of this equation. This is why we wanted to separate the x's and the y's. So here I have an integral with just y's in it times dy, so we can find the integral here. And then the same thing on the right-hand side. I have the integral of negative 2x, it's just x's, times dx. So we're finding some indefinite integrals, so we can use our regular antiderivative rules. The antiderivative of our exponential is just itself, so that's just going to be e to the negative y. But we do need to think about our coefficient out front. Because I have a negative on the y and the exponent, I am going to include the negative out front to make sure that this simplifies properly. On the other side, the antiderivative of negative 2x, we are going to increase the exponent by 1. So we'll go up to x squared. Now thinking about the coefficient to make sure this simplifies, we would be dividing by 2. I have a 2 out front already, so that's just going to simplify to 1. But that negative will stay. And because these are indefinite integrals, we need our constant c. And notice here, I'm only writing c on one side of the equation. Because the constant c is arbitrary, it can be any constant, I don't need to include it twice. because it's arbitrary, if I take the c that would be on the left-hand side and I add that to the constant on the right-hand side, it's still arbitrary, so we only need to include it once. The other thing I can do here is I have a negative on the left-hand side, a negative on the right-hand side, so why don't we multiply the entire equation by -1, just to make it a little easier to work with. So e to the negative y is equal to x squared plus c. And again, the constant it's staying positive, even though I multiplied by -1, because the constant is arbitrary, multiplying by -1 is not going to change it. So this is our general solution here. So when we're asked to find the general solution for a differential equation, this is what we're looking for. And because that constant here is arbitrary, this represents a family of equations that works for our differential equation. So I could pick out several different values for this constant. Each one of those is going to give me a different specific equation that would result in this differential equation. And that's sort of what letter B is talking about here. Find the particular solution that y equals 2 when x equals 1. So we want to find the particular equation based on my general solution that has these two parameters. So essentially what I'm going to do is I'm going to use y is equal to 2 and x is equal to 1 to find out what my value is for this constant. So let's just plug both of these in. All right, so we're going to end up with e to the -2 power. And then on the other side, if we plug in 1, we have 1 squared plus c. So this just leaves the only variable is our constant, and we want to find out what that has to be. So if I do a little bit of rearranging here, I'll write this as 1 over e squared. And then 1 squared is just 1, so if I subtract that, 1 over e squared minus 1, that's our value for c. So now if we take this value of our constant, this is some decimal, but I'm going to leave it like this when we plug it into our general solution. So I'm going to go over here and let me rewrite this. We have e to the -y is equal to x squared, and then our constant that we want for this particular solution, 1 over e squared minus 1. So now this equation represents this particular solution that we're looking for. But just to work with this a little bit, I want to get this so that the y is isolated. So I want this written as y is equal to something. So right now we have e raised to a power. So if I want to undo that, we can use the natural log. So that's going to leave me with -y is equal to the natural log of all of this stuff. So x squared plus 1 over e squared minus 1. And then the last step, to undo that negative, let's multiply both sides by -1. So y is equal to the opposite of the natural log of x squared plus 1 over e squared minus 1. And now this equation, this represents this particular solution such that y equals 2 when x equals 1. So we have our general solution here. This represents a family of different equations that work for our differential equation. And when we were given a couple special parameters, we're able to find a particular solution. And then we rewrote this in terms of y. So we have a nice equation that represents that.